Let's begin with a simple but profound question. In a modern CPU, hundreds of instructions may exist inside the processor at the same time. Some are waiting for data, some are waiting for execution units, some are already executing, and some are finished waiting to retire. But here's the key challenge. How does the CPU know when an instruction is finally ready to run? Not later, not earlier, exactly when its inputs are available. Because in an out-of-order processor, instructions are not executed strictly in program order. Instead, the CPU constantly searches for instructions whose operands are ready so it can execute them immediately. This mechanism is what allows modern processors to achieve extremely high instruction throughput. But it raises an important architectural problem. The processor must continuously answer one question: which instructions are ready to execute right now? To understand how this works, we need to explore several internal mechanisms: Operand readiness tracking, dependency resolution, Wakeup logic, issue selection, and the hardware structures that make all of this possible. By the end of this video, you'll understand exactly how CPUs track instruction readiness and how they decide when an instruction can execute. First, let's recall the problem that out-of-order execution solves. Imagine the following instruction sequence. Instruction 1 loads data from memory. Instruction 2 adds 2 registers. Instruction 3 multiplies 2 values.
Instruction 4 depends on the result of instruction 1.
If the processor executed strictly in order, the entire pipeline might stall while waiting for the load instruction to finish. But modern processors avoid this by executing instructions as soon as their operands become available. This is called dynamic scheduling. Instead of waiting for earlier instructions to finish, the processor asks, is this instruction ready to run? If yes, it can execute immediately. Even if earlier instructions are still waiting, this dramatically improves performance. But it also requires a mechanism to determine readiness. And that mechanism begins with understanding dependencies. Every instruction has operands. These operands may come from registers or from memory. An instruction cannot execute until all of its input operands are available. For example, ADD R3, R1, R2. This instruction requires the values of R1 and R2. If those registers already contain valid values, the instruction can execute immediately. But if one of those registers is produced by an earlier instruction that hasn't finished yet, the ADD must wait. This is a true data dependency, also known as a read-after-write dependency. The CPU must track these dependencies so it knows when operands become available. Without this tracking, instructions might execute using incorrect data, and that would break program correctness. Earlier CPUs handled dependencies in a simple way. They relied on pipeline stalls. If an instruction depended on a previous instruction, the pipeline would pause until the result was ready. This was simple, but inefficient. Modern CPUs instead use more advanced dependency tracking mechanisms. And the first key technology enabling this is register renaming. In modern out-of-order processors, architectural registers like racks or R1 are not directly used by execution units. Instead, they are mapped to physical registers. When an instruction writes a register, the rename stage allocates a new physical register. This eliminates false dependencies. But more importantly for our discussion, it also allows the CPU to track when each operand becomes ready. Each physical register has a readiness state. If the register already contains a valid value, it is marked as ready. If it will be produced by an instruction that hasn't finished yet, it is marked as not ready. When a new instruction enters the scheduler, it checks the readiness state of its source registers. If both operands are ready, the instruction can be issued immediately. If not, the instruction must wait. But where does it wait? Instructions that are waiting for operands are stored in a structure called the issue queue, sometimes also called the scheduling queue or reservation stations. This is where the processor keeps instructions that have been renamed but not yet executed. Each entry in the issue queue contains several pieces of information. The operation type,
They made the destination physical register.
the source physical registers, and readiness bits for each operand. These readiness bits indicate whether the operand value is already available. For example, an instruction might enter the issue queue with this state: operand A, ready. Operand B, not ready. That means the instruction must wait until operand B becomes available, but the processor must detect the exact moment when that operand becomes ready. And this is where wake-up logic comes into play. When an instruction finishes execution, it produces a result. This result is written to a physical register. At that moment, the processor marks that register as ready, but that alone is not enough, because there may be many instructions in the issue queue waiting for that register.
So the processor must notify them.
This notification mechanism is called Wakeup. When a result becomes available, the processor broadcasts the physical register identifier. All instructions waiting in the issue queue compare this identifier against their source operands. If a match is found, the corresponding operand is marked as ready. This process is called tag matching, and it happens extremely quickly. A copy. In many CPUs, this comparison happens across dozens or even hundreds of entries simultaneously, which means the hardware must perform massive parallel comparisons every cycle. This is one of the most complex and power-hungry parts of modern CPUs, but it allows the processor to instantly detect when instructions become ready. Let's walk through a concrete example. Imagine we have 3 instructions in the issue queue. Instruction A produces physical register P5. Instruction B depends on P5. Instruction C depends on P7. Instruction A executes first. When it finishes, the result is written to P5. At that moment, the processor broadcasts the tag P5. Instruction B sees that one of its source operands matches P5.
It marks that operand as ready.
If all operands for instruction B are now ready, the instruction becomes eligible for execution. Instruction C ignores the broadcast because it does not depend on P5. This entire process happens in hardware, and it happens every time an instruction completes execution. Once an instruction becomes ready, it still needs to be selected for execution, because multiple instructions may become ready at the same time, but the processor may have limited execution units. For example, there may only be 2 integer ALUs, 1 floating point unit, 1 load store unit. So the processor must choose which ready instructions to issue. This selection process is handled by the issue logic. The issue logic scans the issue queue every cycle. It looks for instructions whose operands are ready. These instructions are candidates for execution. The processor then selects a subset of them to issue. Selection may depend on several factors: execution unit availability,
Instruction age.
pipeline constraints, and resource conflicts. Some CPUs prioritize older instructions to avoid starvation. Others use more complex heuristics to maximize throughput. Once selected, the instruction is dispatched to the appropriate execution unit, and execution begins. But what happens if an instruction's operands are not ready yet? The instruction simply remains in the issue queue. It waits, and it continues listening for wake-up broadcasts.
Every time an instruction completes execution, a broadcast occurs.
And waiting instructions check whether that broadcast corresponds to their operands. Eventually, when all operands become ready, the instruction becomes eligible for execution. This mechanism allows the CPU to dynamically schedule instructions based on actual data availability, and that's what makes out-of-order execution possible. Now let's discuss an important detail. The low-band readiness is not the same as instruction completion. A register becomes ready as soon as the producing instruction generates the result, but the instruction itself may not retire until much later. Retirement happens in program order through the reorder buffer. This ensures precise exceptions and correct program behavior, but readiness tracking allows execution to happen out of order. So readiness tracking and retirement ordering are separate mechanisms. Both are necessary for correct operation. Modern CPUs implement these mechanisms at enormous scale. An issue queue may contain 32 entries, 64 entries, or even over 100 entries in high-performance designs. Each entry must track operand readiness. Each entry must compare operand tags during wake-up broadcasts, and the issue logic must evaluate readiness every cycle. All of this happens within extremely tight timing constraints, often within a single clock cycle. This makes the issue queue one of the most challenging structures in CPU design. It consumes significant power, and it places strict limits on clock frequency because the hardware must perform large numbers of comparisons extremely quickly. For this reason, many modern CPUs use sophisticated optimizations. Some processors partition the issue queue into multiple smaller queues, or others use distributed reservation stations. Some designs restrict wake-up broadcasts to reduce power consumption, and many processors use hierarchical scheduling structures. These optimizations reduce hardware complexity while maintaining high performance. But the core principle remains the same: track operand readiness, detect when operands become available, and issue instructions as soon as they are ready. Another interesting case occurs with memory operations. Loads and stores may depend on memory addresses rather than registers. In these cases, readiness depends on address calculation and memory ordering rules. The CPU must ensure that loads and stores execute in a safe order. This requires additional mechanisms like load queues, store queues, memory dependency prediction. But even in these cases, readiness tracking still plays a key role, because a load cannot execute until its address is known, and a store cannot commit until earlier memory operations are resolved. So readiness tracking extends beyond registers into the memory subsystem. Let's summarize the process. An instruction enters the pipeline. Register renaming assigns physical registers. The instruction enters the issue queue. Each operand has a readiness state. If operands are not ready, the instruction waits. When a producing instruction finishes execution, it broadcasts its result tag. Waiting instructions compare this tag with their source operands. Matching operands become ready. Once all operands are ready, the instruction becomes eligible for issue. The issue logic selects ready instructions and sends them to execution units. Execution begins. This cycle repeats continuously
Every clock cycle.
across dozens or hundreds of instructions simultaneously. Without this readiness tracking system, modern CPUs would not be able to execute instructions out of order. The processor would be forced to stall whenever a dependency occurred. Instead, readiness tracking allows the CPU to dynamically exploit instruction-level parallelism. And that's one of the fundamental techniques that allows modern processors to achieve high performance. It's also one of the reasons modern CPU cores are incredibly complex pieces of engineering. What appears to be a simple instruction stream at the software level becomes a massive hardware scheduling problem inside the processor, and yet all of it happens invisibly, billions of times per second. In the next video, we'll go even deeper into the scheduling hardware that makes this possible. We'll examine the structure that actually stores waiting instructions and tracks their readiness in detail. And we'll explore one of the most important components of modern out-of-order CPUs, reservation stations. Because while we've talked about the concept of issue queues and scheduling logic, the exact structures used by different CPU architectures can vary significantly. And understanding reservation stations reveals even more about how modern processors achieve high instruction throughput. If you want to understand how software really runs on modern hardware, these internal mechanisms are essential, because every compiled program you run ultimately depends on these scheduling systems to execute efficiently. And once you understand how CPUs detect instruction readiness, you're one step closer to understanding how modern processors actually work.